Hyperthreading, officially called hyperthreading technology or HT technology, and abbreviated as HTT or HT, is Intel's proprietary simultaneous multithreading (SMT) implementation used to improve parallelization of computations, doing multiple tasks at once, performed on x86 microprocessors. It first appeared in February 2002 on Xeon server processors and in November 2002 on Pentium 4 desktop CPUs. Later, Intel included this technology in Itanium, Atom, and Core I series CPUs, among others. For each processor core that is physically present, the operating system addresses two virtual, logical, cores and shares the workload between them when possible. The main function of hyperthreading is to increase the number of independent instructions in the pipeline. It takes advantage of superscalar architecture, in which multiple instructions operate on separate data in parallel. With HTT, one physical core appears as two processors to the operating system, allowing concurrent scheduling of two processes per core. In addition, two or more processes can use the same resources. If resources for one process are not available, then another process can continue if its resources are available. In addition to requiring simultaneous multithreading (SMT) support in the operating system, hyperthreading can be properly utilized only with an operating system specifically optimized for it. Furthermore, Intel recommends HTT to be disabled when using operating systems unaware of this hardware feature. Hyperthreading technology is a form of simultaneous multithreading technology introduced by Intel, while the concept behind the technology has been patented by Sun Microsystems. Architecturally, a processor with hyperthreading technology consists of two logical processors per core, each of which has its own processor architectural state. Each logical processor can be individually halted, interrupted, or directed to execute a specified thread, independently from the other logical processor sharing the same physical core. Unlike a traditional dual processor configuration that uses two separate physical processors, the logical processors in a hyperthreaded core share the execution resources. These resources include the execution engine, caches, and system bus interface. The sharing of resources allows two logical processors to work with each other more efficiently, and allows a logical processor to borrow resources from a stalled logical core, assuming both logical cores are associated with the same physical core. A processor stalls when it is waiting for data it has sent for so it can finish processing the present thread. The degree of benefit seen when using a hyperthreaded or multi-core processor depends on the needs of the software, and how well it and the operating system are written to manage the processor efficiently. Hyperthreading works by duplicating certain sections of the processor, those that store the architectural state but not duplicating the main execution resources. This allows a hyperthreading processor to appear as the usual physical processor and an extra logical processor to the host operating system. HTT unaware operating systems see two physical processors, allowing the operating system to schedule two threads or processes simultaneously and appropriately. When execution resources would not be used by the current task in a processor without hyperthreading, and especially when the processor is stalled, a hyperthreading-equipped processor can use those execution resources to execute another scheduled task. The processor may stall due to a cache miss, branch misprediction, or data dependency. This technology is transparent to operating systems and programs. The minimum that is required to take advantage of hyperthreading is symmetric multiprocessing (SMP) support in the operating system, as the logical processors appear as standard separate processors. It is possible to optimize operating system behavior on multi-processor hyperthreading capable systems. For example, consider an SMP system with two physical processors that are both hyperthreaded, for a total of 4 logical processors. If the operating system's thread scheduler is unaware of hyperthreading, it will treat all 4 logical processors the same. If only 2 threads are eligible to run, it might choose to schedule those threads on the 2 logical processors that happen to belong to the same physical processor. That processor would become extremely busy while the other would idle, leading to poorer performance than is possible by scheduling the threads onto different physical processors. This problem can be avoided by improving the scheduler to treat logical processors differently from physical processors. In a sense, this is a limited form of the scheduler changes that are required for NUMA systems. According to Intel, the first hyperthreading implementation used only 5% more die area than the comparable non-hyperthreaded processor, but the performance was 15–30% better. Intel claims up to a 30% performance improvement compared with an otherwise identical, non-simultaneous multithreading Pentium 4. Tom's Hardware states, in some cases a P4 running at 3.0 GHz with HT on can even beat a P4 running at 3.6 GHz with HT turned off. Intel also claims significant performance improvements with a hyperthreading-enabled Pentium 4 processor in some artificial intelligence algorithms. Overall, the performance history of hyperthreading was a mixed one in the beginning. As one commentary on high-performance computing from November 2002 notes, hyperthreading can improve the performance of some MPI applications, but not all. Depending on the cluster configuration and, most importantly, the nature of the application running on the cluster, performance gains can vary or even be negative. The next step is to use performance tools to understand what areas contribute to performance gains and what areas contribute to performance degradation. As a result, performance improvements are very application dependent. However, when running 2 programs that require full attention of the processor, it can actually seem like one or both of the programs slows down slightly when hyperthreading technology is turned on. This is due to the replay system of the Pentium 4 tying up valuable execution resources, equalizing the processor resources between the 2 programs, which adds a varying amount of execution time. The Pentium 4 Prescott and the Xeon Nocona processors received a replay queue that reduces execution time needed for the replay system and completely overcomes the performance penalty. According to a November 2009 analysis by Intel, performance impacts of hyperthreading result in increased overall latency in case the execution of threads does not result in significant overall throughput gains, which vary by the application. In other words, overall processing latency is significantly increased due to hyperthreading, with the negative effects becoming smaller as there are more simultaneous threads that can effectively use the additional hardware resource utilization provided by hyperthreading. A similar performance analysis is available for the effects of hyperthreading when used to handle tasks related to managing network traffic, such as for processing interrupt requests generated by network interface controllers, NICs. Another paper claims no performance improvements when hyperthreading is used for interrupt handling. When the first HT processors were released, many operating systems were not optimized for hyperthreading technology, e.g. Windows 2000 and Linux older than 2.4. In 2006, hyperthreading was criticized for energy inefficiency. For example, specialist low-power CPU design company ARM stated that simultaneous multithreading, SMT, can use up to 46% more power than ordinary dual-core designs. Furthermore, they claimed that SMT increases cache thrashing by 42%, whereas dual-core results in a 37% decrease. Intel disputed this claim, stating that hyperthreading is highly efficient because it uses resources that would otherwise be idle or underutilized. In 2010, ARM said it might include simultaneous multithreading in its future chips. However, this was rejected in favor of their 2012 64-bit design. In 2013, Intel dropped Summit in favor of out-of-order execution for its Silvermont processor cores, as they found this gave better performance with better power efficiency than a lower number of cores with SMT.